my last class, we found that the 6 active states of the inverter occupy 6 corners of the hexagon, okay, and 2 zero vectors, which are also known as null vectors, they are at the origin. See in this figure, see 0 0 0 or 1 1 1 corresponds to the origin. Just by turning on the upper switch of phase A, okay, or for 0 0 1, the magnitude of the space vector is Vs at an angle 0, okay. Magnitude of the space vector is Vdc at an angle 0, okay. Now turning on the upper switch of phase B, the space vector moves by an angle 60. See 0 1 1, the magnitude remains the same, is equal to the magnitude of the DC link voltage, Vdc, but it moves by 60 degrees. Now by turning off the upper switch of the phase A, okay, it moves by another 60 degrees. See here, it is 0 1 0. And now turning on the upper switch of phase C, it moves by another 60 degrees, and so on, okay. So another observation that we made was that if all 3 phase voltages are sinusoidal, then the locus of Vs is a circle, okay. Now what about the space vector PWM technique? In space vector PWM technique, okay, the space vector, the required space vector is synthesized using 2 adjacent vectors and the null vector, okay. See in this figure, assume that the space vector is in quadrant 1 or in between V1 and V2, okay, and making an angle theta. The length of the space vector is determined by the V by F curve, okay. Now we need to synthesize using V1, V2 and this null vectors in such a way that volt second balance is satisfied, okay. In other words, Vs into time Tc equal to V1 and T1 plus V2 into T2, where T1 is the time for which V1 is applied, T2 is the time for which vector V2 is applied, and the relationship between Tc, T1 and T2 is given by this equation. See, Tz is the time for which 0 vector is applied, okay, is Tc minus T1 plus T2, and Tc is Ts by 2, okay, where Ts is the sampling time, okay. During this time it is assumed that Vs remains stationary at that particular point. I will repeat, Tc is Ts by 2, where Ts is the sampling time, okay. During this time the space vector Vs is assumed to be stationary at that particular point. Okay. So, by solving these equations, we found that T1 is given by this equation and T2 is given by this equation. So, to determine T1 and T2, I need to know only theta, or the position of the space vector in the sector. Okay, I need to know only this angle theta. Now, Tz can be applied either by using 0 0 0 or 1 1 1. Okay. The time for which, or the way 0 0 0 or 1 1 1 is applied is not going to affect the volt second balance. Okay. It is only during the active vectors, or is only when the active vectors are applied, the inverter supplies power to the load. Okay. So duration for which 0 vector is applied, or duration for which 0 0 0 or 1 1 1 is applied can be chosen as per convenience. Okay. Now, coming to the implementation part, at any given time only one switch is turned on or off. Okay. That is the space vector requirement, space vector PWM technique requirement. Okay. So, we will start with 0 0 0. In other words, we are at the origin. By turning on phase A alone, the upper device of phase A alone, space vector moves along the x axis. Okay. See here, 0 0 0 is applied for Tz by 2 duration. Okay. I have taken this for as convenience. It is not a must that I should apply this 0 0 0 vector for Tz duration. See, after some time I am turning on the upper device of phase A. See, phase B, phase C, the upper devices are still off, the lower devices are on. So, this is nothing but 0 0 1. Okay. So V1, this is the V1 vector is applied for T1 duration. Okay. So, at the end of T1, I am turning on the upper phase of upper device of phase B. Okay. So, that is 1 1 0, or C phase is 0, B phase is 1, A phase is 1. Okay. And at the end of T2, I am turning on the upper device of phase C also. See, now it is 1 1 1. Okay. So, and this is entire TC period. Okay. So, see the sequence 0 0 0 to 0 0 1, and from there 0 1 1 and again 1 1 1. Now, this is TC period, and the relationship between the sampling time Ts and Tc is twice Tc is Ts. Okay. Now, again at any given time only one switch should be turned on or off. So, we were at this point with 1 1 1, I will continue to apply the same vector for another Tz by 2 period. Okay. I will apply the same vector 1 1 1 for another Tz period. So after some time I will turn off the upper phase, I will turn off the upper device of phase C. I have turned off here the upper device of phase C. Phase A is 1, phase B is 1, phase C is 0. So this is for T2 period, okay. This is for T2 seconds. At the end of that period, I will turn off the upper device of phase B, okay. See here, A phase is 1, B phase has become 0 and C phase is 0. This is 0 0 1, okay. And after T1 seconds I will turn off the upper device of phase A. So I have 0 0 0. So one complete cycle I have completed for sampling period. So I started with 0 0 0, 0 0 1, 0 1 1 and to 1 1 1 and again backwards, okay. So this is about the space vector PWM technique, wherein only one device is being turned on or off. Now what is the maximum value of m for which the space vector is sinusoidal? How do I determine the maximum, the length of the vector for which all three phase voltages are sinusoidal? I told you that if all three voltages are sinusoidal, the locus of Vs is circular, okay. So for lower modulation index value, Vs will always remain within the hexagon, okay. Now what is the maximum value of Vs for which or beyond which the voltages are going to be non-sinusoidal, okay. How do I determine? See here, right, the maximum value of Vs for which the locus is circular is the diameter of the encircling circle, okay. So the radius of this circle is the length of Vs for which the space vector or for which all three voltages are sinusoidal, okay. Now what is the value of the radius of this circle, okay. This is nothing but, see, this is an hexagon encircling circle, okay. So length of or the radius of the circle is VDC into cos 30, well, see this angle is 30 degrees, so that is equal to root 3 by 2 into VDC, okay. Now I will define a term MF, okay, is equal to V1SP divided by V1S, where V1SP is the peak of the fundamental component of the phase voltage using space vector PWM technique, okay, where V1SP is the peak of the fundamental component of the phase voltage obtained using a PWM technique, and V1S is the peak of the fundamental component of the phase voltage obtained using square wave operation, okay. So MF is the ratio of V1SP divided by V1S. Now what is V1S, or in other words, what is the peak of the fundamental component of the phase voltage got using a square wave operation, okay, that we have already calculated in maybe last lecture or for that. We found that it is 2 VDC by pi, 2 VDC by pi. Now what is V1SP? See, Vs star maximum, or the maximum value of Vs is root 3 by 2 into VDC, okay. I will repeat, maximum value of the space vector is root 3 times VDC, okay, because this is the radius of the circle, okay, which lies inside the hexagon. Under that condition, all three voltages are sinusoidal. Now what is the relationship between Vs and the phase voltages? If VAN, VBN, VCN are known, you can calculate Vx and you can calculate Vy, and therefore Vs. I will repeat, if I know VAN, VBN, VCN, you can calculate Vx and Vy, the x axis component and the y axis component of all the three phases, and therefore you can calculate the length of the space vector Vs. But I have not told you how to determine VAN, VBN, VCN if Vx and Vy are known, okay. So because I need to calculate three values, VAN, VBN, VCN, and I know only Vx and Vy. How do I calculate VAN, VBN and VCN? There exists a relationship. See, here is the relationship. VAN is equal to 2 by 3 into Vx, okay. So there is a way to derive this. I am not going to tell you how to derive this relationship, okay. So but then it can be derived. So therefore VAN is equal to 2 by 3 into Vx, VBN is given by minus 1 3 Vx plus 1 over root 3 into Vy, okay, and VCN is equal to minus 1 3 Vx minus 1 of square root 3 Vy. So if I know Vx and Vy using these three relationship, you can calculate the value of VAN, VBN and VCN. Okay. Now what is the peak value of the phase voltage that I can get using the space vector? Okay. We found that for 0, 0, 1, in other words, only the upper device of phase A is on, the length of the space vector is VDC, okay. and for this position y component is 0. We have only the x component. Okay. See, I will show you this position corresponds to 0, 0, 1 somewhere here. See here, this is a 180 degree conduction, VS0, VB0, VC0, and these are the 3 phase sinusoids. Okay. For 0, 0, 1, we found that VAN is 2 by 3 VDC, okay, and VBN and VCN, they are same, minus 1/3 VDC. Recall, for 0, 0, 1, VAN is 2 by 3 VDC, and VBN and VCN, they are same but minus 1/3 VDC. Okay. Now, in this figure, in this 3 phase sinusoids, where this point corresponds to, I said VBN and VCN are same, both are negative, and the value is 1/3 VDC. VBN and VCN are both are same and they are negative. Definitely this point is thus. See, VBN and VCN, they intersect at this point, okay, and both are negative. And at this point, VAN is at the peak. VAN is at the peak. Okay. So, definitely 0, 0, 1 position, at that point phase A is at the peak. Okay. Now, what is the relationship between Vs and the phase voltage? So, Vs is equal to 3 by 2 times VAN. Okay. Now, so for 0, 0, 1, Vs is equal to only Vx, okay, and that is equal to VDC. And in my last class, I have derived an expression wherein Vx is equal to 3 by 2 times VAN. See, I will repeat. For 0, 0, 1, Vs is equal to Vx, Va by is 0, and that is equal to VDC itself, and the relationship between Vx and VAN is this: Vx is equal to 3 by 2 times VAN. So, therefore, VAN is equal to 2 by 3 times Vs. Okay. So, what is the peak value of VAN? It is nothing but 2 by 3 times the peak value of Vs that can be obtained. Okay. So, it is 2 by 3 into 3 by 2, square root of 3 by 2 into VDC. So, the peak of the phase voltage VAN that can be obtained using space vector PWM technique is 0.577 VDC. Okay. I will repeat, peak of the phase voltage VIN, that is also equal to VBN, that is also equal to VCN, is 0.577 times VDC. So, what is the value of MF? It is nothing but the peak of the phase voltage using space vector PWM technique to the peak of the fundamental component using square wave operation. That is this 0.577 VDC divided by 2 by pi into VDC. So, this is equal to 0.907, okay, 0.907. So, how do I interpret this result? I can say that 90.7% of the fundamental of square wave is available using space vector PWM technique. I will repeat, 90.7% of the fundamental of a square wave is available compared to only 78.5% in sinusoidal PWM technique. So, I will repeat, I found the ratio of the fundamental in space vector to square wave is 0.907. Okay. So, if I take the peak of the fundamental that is obtained using a square wave is 1 per unit, okay. So, I am getting 90.7% in space vector. How much are we getting in sinusoids PWM technique, sinusoidal PWM technique? Or what is the peak of the sinusoidal PWM technique, peak of the fundamental using sinusoidal PWM technique? It is VDC by 2. See, peak of the fundamental component, the phase voltage in sinusoidal PWM technique is VDC by 2. See, I will repeat, peak of the fundamental component of the phase voltage in sinusoidal PWM technique is VDC by 2. Okay. So, this ratio comes up to be 78.55%. Okay. So, in space vector it is 90.7, in sinusoidal PWM technique it is 78.55%. Okay. So, looks like in space vector PWM technique it is possible to get higher value of the fundamental component. By the way, we have also done third harmonic injected PWM technique. What did we find? See, we added 15% more for the fundamental. In addition, we added a third harmonic component also, 0.19 times sin 3 omega t. So, our modulating wave was 1.15 sin omega t plus 0.19 into sin 3 omega t. So, I said third harmonic components do not appear in line to line voltage waveform. So, fundamental component is proportional to the sinusoidal modulating wave. So, since it is 1.15, so there is going to be a 15% increase in the phase voltage. So, if I take this ratio in third harmonic injected PWM technique, it is sinusoidal is 78.55 into 1.15. Okay. So, it is comes out to be 0.907, same as same as space vector PWM technique, same as space vector PWM technique. In other words, the peak of the fundamental component of the phase voltage that can be obtained using space vector PWM technique is the same as the peak of the fundamental component of the phase voltage using third harmonic injected PWM technique. So, in other words, space vector PWM technique is almost the same as third harmonic injected PWM technique. Okay. Yeah, I had told you that if you complete one cycle in 6 steps, you will get 6-step operation, okay, wherein the space vector moves by an angle 60 degrees at a time. To have smooth operation, I said we need to divide the entire 360 degrees by large number of parts. I said we need to digitize a sine wave. In other words, the sampling time Ts should be as small as possible, because we have assumed that during that period or during Ts seconds, space vector is stationary. Now, how many samples in one sector? How do I decide on the number of samples in one sector? Or what is the rule to be followed? The rule to be followed is that all sectors should be equally used in the entire cycle for producing symmetric line voltage. I will repeat, all the sectors should be equally used in the entire cycle for producing the symmetric line voltage. So, in other words, the samples are positioned symmetrically about each sector, okay, with one sample at the sector and the center. I will repeat, the samples are positioned symmetrically about each sector, okay. The number of samples should be symmetric about each sector with one sample at the center, with one sample at the center. So, therefore, if there are 3 samples in one sector, they should be positioned at one at 10 degrees, another one is at 50 degrees, because they should be symmetric, one at the center. So, that is at 30 degrees. So, in every sector, if I have one pulse at 10, I should have another pulse at 50, and at another one is at the center, 30 degrees. Okay. So, this is the rule should be followed. All the sectors should be equally used in the entire cycle. Only then I can have symmetric line voltage. Samples, they should be positioned symmetrically about each sector. One pulse here, one at the center, one at the center. Okay. And it should be, number of pulses should be odd multiple of 3. Odd multiple of 3. Okay. 3, 9 and so on. Okay. So, this rule has to be followed while implementing space vector PWM technique. So far we discussed 4 different types of PWM techniques. What are they? One is sine triangle, third harmonic injected PWM technique, harmonic elimination, and last one is space vector PWM technique. See, all these PWM techniques, they control the output voltage of the inverter. Okay. In other words, the voltage applied to the load is being controlled. Now, current will flow depending upon the circuit conditions. Okay. So, voltage is dependent variable and current varies independent depending upon the circuit condition. By the way, you cannot control both voltage as well as current in one circuit. Now, if it is possible to control the output voltage, it is also possible to control the current that is flowing in the circuit. Okay. So, there is a PWM technique which is known as hysteresis current controlled PWM technique. Okay. I will repeat this hysteresis current controlled PWM technique. What it says? It says, take a reference, a sinusoid current, okay, of required magnitude and required frequency. Okay. See, magnitude depends on the circuit condition or load requirement. Okay. Frequency of the sinusoid or frequency of the reference current is the same as the frequency of the fundamental component of the voltage applied to the machine. Okay. Now, you have generated a reference sinusoid which is the required current that should flow in the machine. Okay. But then in a power electronic equipment, if there is switching, it is just not possible to have a pure sinusoid current flowing into the machine. Okay. It is rather impossible to have a pure sinusoid current flowing into the machine because there are switchings. So, the moment when you close the switch, current may increase or decrease, but then you can always control the variation in current. Okay. So, in hysteresis current controlled PWM technique, there is a reference sinusoid, there is a upper band and there is a lower band. See here, I will show you. So, this is the reference current I reference, which is a sinusoid, okay, a full sinusoid, okay, of required magnitude and frequency. Then I will take a upper band IU star, which is equal to I reference plus some hysteresis band HB. HB stands for the hysteresis band. Similarly, the lower limit IL star is IREF minus the hysteresis band. In other words, current is controlled, or current that is flowing in the load is controlled within these two bands. Okay. I told you, it just cannot have an ideal sine wave, pure sine wave current. Okay. But then you can always control the variation in the current. So I have taken an upper band and a lower band, and current should be controlled within this band. Okay. How do I control this current? By the way, I have covered this in AC to DC conversion, unity power factor conversion. I had covered this. Okay, I will just repeat it. Okay. There may be the reference current that I have taken may be a rectified sign, because we control the DC link current. Okay. We had placed the inductor in the DC side and we had controlled that current. Here the current that is flowing into the load or output current of the inverter that we are controlling. Remember, we are controlling the output current of the inverter flowing into the load, that we are controlling. Definitely it has to be AC. Okay. So how to control the current within the hysteresis band? So when the actual current touches the lower band, you close the upper switch and open the lower switch. See, when I close the upper switch, VA0 is plus VDC by 2, remember, and if I close the lower switch, VA0 is minus VDC by 2. So definitely when I close the upper switch, current should increase. Okay. So I will close the upper switch till this current or the current flowing into the load increases and touches the upper band. Okay. And when it touches the upper band, I will open the upper switch and close the lower switch. Now the voltage applied is minus VDC by 2. Current reduces. See here. When it's touched upper switch, sorry, when it's touched the upper lower band, so this is the lower band, this is the upper band. When it's touched the lower band, I close the switch. So VA0 has become positive here. Current increases. When it touched the upper band, you open the upper switch and close the lower switch. So this is it, closed the lower switch. Voltage applied is minus VDC by 2. You wait till this current comes and touches the lower band, and so on. Okay. So in the block diagram level, it looks something like this. I have shown a motor here, does not matter, it could be anything. Inverter, this implies that we are sensing the current flowing into the load. Okay. There is the IA actual and this is the reference current. Okay. A reference sinusoid. Okay. This is the actual. Plus minus. What do I get? I will get the error. And this error should lie within this hysteresis. This is HB, this is also HB. And the signals go to the driver circuit to turn on and off the switches. By the way, this hysteresis band is nothing but a Schmitt trigger. Okay. So this is a subtractor, op amp again, op amp circuitry. This is another a Schmitt trigger. I have shown you here only for one phase, and I showed you there are 3 sensors or 3 current sensors to measure the instantaneous current that is flowing into the machine. Remember, it is the instantaneous current that is flowing into the machine that is controlled. Okay. See, you do not need to have 3 current sensors. You can do with just 2 current sensors, because in 3-phase 3-wire system, the current that is flowing in the third wire is the sum of these two. In other words, IA plus IB plus IC is equal to 0. So, IC is minus of IA plus IB. So, you can implement this circuit using just 2 current sensors. Okay. So, what is the advantage of this scheme over the other PWM techniques wherein voltage is being controlled? See, here we are controlling the current. It is the current that is flowing into the machine will determine the torque. See, for example, in a DC machine, the armature current that is flowing will decide the torque that produces. T is K phi into Ia, not the armature voltage. Okay. So, by controlling the current that is flowing into the machine, it is possible to control the torque directly. Okay. So, in other words, a current controlled machine responds faster compared to a voltage fed machine, because I am directly controlling the current. Okay. No, I am not applying the voltage and thereby current increase. No, here the current is directly being controlled. So, current fed load responds faster compared to voltage fed. And the second advantage is, so there is inherent overload protection. There is inherent overload protection. We are sensing the current and controlling within a reference value, There is nothing like current inrush as in the case of voltage fed machines. Okay. Here current is directly being controlled. There, see, when I am changing the modulation index, okay, there could be inrush current, because voltage applied to the machine has changed, or if modulation has suddenly increased, however low it may be, so applied voltage has increased. Okay. The other circuit conditions may not change that fast. Okay. So, there could be, or there is inrush current in almost all the voltage fed PWM techniques. This is absent in current fed machine or hysteresis current controlled PWM technique. Okay. What could be the other advantage of current controlled PWM technique? See, the input to the inverter is a voltage source, okay, and this VDC voltage source is being derived by rectifying the input AC. So, if input AC fluctuates, which generally is, so DC link also will fluctuate, and if DC link fluctuates, and assuming that I have already programmed my V by F curve in the controller, okay, the flux in the machine will change now. So, I will repeat, I have programmed some V by F curve in the microcontroller used in the inverter, and assume that I am not sensing the DC link voltage, I am assuming that DC link voltage is held constant. Because of the variation in the input voltage, input AC voltage, the rectified DC voltage also is reduced, or so therefore, the input voltage to the inverter is also reduced, and the controller does not know anything about the reduction in the input DC. So, definitely there is going to be a change in the flux in the machine, because I may be keeping V by F constant, okay. You may be keeping V by F constant, but then that V itself has changed, because VDC itself has changed. Whereas in current control PWM technique, what happens? It does not matter whether the DC link voltage is fluctuating or not, we are controlling the current. Current is being controlled within a hysteresis band. Okay. So, as long as the current touches the upper band, switch is being closed, and as long as the current touches the lower band, the bottom switch is closed. So, a inverter with current control is almost insensitive to the fluctuation in the DC link, whereas any other voltage control PWM techniques, if you do not sense the DC link voltage, the V by F ratio, even if you keep it constant, the value of V itself has changed, therefore flux may not be the rated value, flux may not be the rated value. Okay. Now, how do you choose this hysteresis band? Smaller the band, okay, the waveform will be superior, because current that is flowing into the machine is controlled within a hysteresis band, and that band itself is very small. So, you may have approximately a sine wave itself, almost an ideal sine wave, but then smaller the band, higher will be the switching frequency, because see in this figure, if this band is very small, current touches the lower band, immediately I need to close the upper switch, current increases, band is very small, it touches the upper band, immediately I need to open that switch and close the lower switch. So, smaller the band, waveform is superior, but then switching frequency is higher, switching frequency is higher, and just the opposite, or higher the band, waveform deteriorates, switching frequency is low. So, it depends on the power level, the devices that you are using will decide the height of the hysteresis band. Okay. So, a last point to be noted here is that, so this is an inverter, a voltage source inverter, okay. Input is an ideal voltage source, assumed to be ideal voltage source, but then you are controlling the current flowing out of the inverter, okay. So, as a voltage source with current control, voltage source with current control, okay. This is quite popular in electric drives, especially high performance electric drives, okay. Voltage source with current control is quite popular. So, more about or more on inverters we will study in our next class. Thank you.